going to give us a talk on the numerical study of the interaction of vortex structures in plasmas and fluid. He is a professor at Kazan Federal University in Russia.
Today I'd like to discuss the problems associated with theory and modeling of dynamics of vortical structures in continuous media and some applications in real physical media. After some introduction remarks, we'll write basic equations in general approach and tell about physical sense of these equations for different applications. After that, we'll consider numerical simulation of dynamics of the vortical structures on the basis of modified method of contour dynamics, and further discuss some applications in the atmosphere and hydrosphere, and also in a plasma, and in some other possible applications. Vortical motions of a wide spectrum of scales, from a microcosm up to the universe, surround us everywhere. The most interesting examples, which can be resulted here in the context of theme of this talk, are the following: cyclones and anticyclones in the atmosphere, tropical cyclones and tornadoes, vortical structures in atmospheres of other planets. Here you can see Jupiter's red spots, spiral structures of galaxies, oceanic vortices, vertical loops and tubes in solar corona, etc. It's the important fact. Despite a variety of the physical nature of vortical motions, practically all of them can be described by one enough general model, and it allows to treat vortical processes in various physical media as consequences of the uniform general theory of a vortical motion, by analogy to the theory of fluctuations or theory of waves. So we shall use such approach here and consider on its basis the problems of simulation of vortical structures and application of such investigations. Well, basic equations in general approach. The Euler equation for incompressible inviscid fluid in two-dimensional case, in case of flat motion, takes the form of these set of equations. And here the equation of continuity. Here first term equals 0 for ideal incompressible fluid. Introduce the flow function, where U and S are fluid velocity and displacement. And we can write the function zeta, which has a sense the vector of vortex, and for flat motion it is a vorticity. Euler equations in new variables, vorticity and flow function, take the following form, where last term equals 0 from equation of continuity for flat motion. And we can write equation of carry of a vortex in this form, where the two last terms describes convection. Vortex is carried by a string. We write equation for vorticity in the following form, and now we can write the Poisson equation for flow function. A simple model of two-dimensional magnetized plasma of Taylor-McNamara is a charged filaments aligned in a uniform magnetic field which move with the central directed velocity. Here, set of equation. Here, EI is a charge on unit of length, and H is Hamiltonian, which has a sense of energy of long interaction. In a continuous limit, this two-dimensional plasma satisfies to this set of equations, where ρ is the charge density. You can see that these equations are identical to the equations for two-dimensional motion of indices in compressible fluid. In this case, function ρ is the z component of vorticity, and psi function is a flow function. Equations of motion of fluids of ideal ionospheric plasma have a similar form. Another two-dimensional continuous models include the Debye radius of shielding in the Poisson equation. In these models, the Hamiltonian takes the following form and describes the shielded interaction between filaments. Next model, the model of Hasegawa-Mima, includes the ionic polarized current through the equation of motion of ions. In this case, key is not Debye length, but it's ion Larmor radius from temperature, and shielding is an indirect effect of the ion polarized current. The model of hydrodynamical fluids, Charlie, describing the motion of the atmosphere, also corresponds to shielding interaction. Atmospheric currents in a horizontal plane are described by this equation, where h is the atmospheric depth and r is the Coriolis force. Here, a rho of length of shielding plays the Rossby radius. Thus, the set of equations describing the motion of fluid, gas, or plasma in generalized variables has the following form. The sense of the variables in dependence on type of medium is shown in this table. For example, function ρ has a sense of z component of vorticity for fluid and gas, and it has a sense line density of a charge for a plasma. Numerical simulation. For numerical simulation, we used specially developed modified quantum dynamics method. The CD method is based on the following assumptions. Vortex is rotated as a wall. Each point of the contour interacts with each point of the same contour and with each point of other contours. Omitting details, let's note only that from Poisson equation we have the flow function. Here is a green function. Further integrating, we obtain for velocity this equation. Changing all the coordinates of the contour points with time is the solution of these differential equations. For numerical simulation, for sampling, we use the three-layer scheme in this form. Stability condition for this scheme is given by this inequality. I should say that CD algorithm is rather simple and doesn't take such time expenses as, for example, the algorithms based on the direct solution of the Navier-Stokes equation. Let's consider our results on the n-vortical interaction. Left picture shows a scheme of initial configuration of the system of two vortices. We have obtained the generalized critical parameters xi and found numerically its critical value for 2 and 4 vortical systems for any initial cases, initial states. We have found that two possible regimes can take place. If xi is less than its critical value, we observe the vortex deformation with a quasi-recurrence phenomenon, this movie. And in opposite case, the regime of the phase intermixing is realized. That ends by transit to turbulent regime. Other critical parameter delta is the distance between boundaries of vortices. For vortices with the same polarities, the result of evolution depends on this critical parameter. For example, for rather big delta, they, on a level with rotation about their own axis, rotate around of common center. The interaction is weak and it's reduced to a cyclic change of the shape. So we have quasi-recurrence phenomenon. This picture. For rather small delta, the vortices on a level with the same rotations interact, forming a common vortex region, which consists of the vorticities of more small scales. And the regime of active interaction with the phase intermixing takes place. We have found that critical initial distance for two interacting vortices, dividing these two types of interaction, is the following, where d is the vortex diameter. Here you can see intermediate case. So, for vortices with opposite polarities, we observe that they practically don't interact independently on value of the distance between boundaries of vortices. We have considered also the problem with n equals 3 and 4. So 3 vertical and 4 vertical systems in two variants. For vortices linearly disposed at initial time and for vortices disposed in the corners of appropriate equilateral figure at initial time. For other big and equal initial distance between vortices, the evolution leads to formation of two vorticity regions. As a result of more strong interaction of each of the outer vortices with the closest inner vortex. Thus, the interaction of forming pairs is similar to that of two vortex cases. In opposite case, we observe the formation of a complex vortex structure, which consists of many vorticities of more small scales. The evolution leads to formation of complex turbulent field. We can also see that the interaction between outer vortices is strong. This is critical value of critical parameter delta. We also simulated the interaction dynamics of the three-dimensional plane rotating vortex structures with a two-dimensional approximation within the framework of many-layer model of medium. You can see numerical simulation of interaction of two three-dimensional vortices with the exponential decreasing of the vorticity with the coordinates. One can see that in the beginning the vortices, the central regions, start to interact, and only then other areas are involved in interaction. Such behavior is explained by stronger interaction of central regions, which locate at a relatively short distance each other, and their vorticities have relatively big values, so that the ratio zeta to delta is big in comparison with z for top and bottom of vortices. And now I'll show some examples of our results on simulation of vertical motions in the atmosphere and hydrosphere and vertical structures in plasma. Vertical motions, first example of vertical motions in the atmosphere and hydrosphere. You can see in this picture modeling of evolution of the cyclonic type synoptic vortex, numerical result, left panel, and satellite photograph. In this picture you can see modeling of the four vertical interaction in channel orbiter in Japan, numerical result, and air photograph. You can see that our numerical results are qualitatively coincided with modeling real system. We have fulfilled simulation of the tornado evolution with use of quasi-two-dimensional approach with many-layer approximation of the three-dimensional vertical structure by the vortex system. Our model vortex has been associated with a real tornado from video record. One can see that our simulation reflects the basic features of evolution of a tornado. In particular, we investigated the influence of the perturbation imposed on the tornado axis on its dynamics. We established, as a result, that small cross-section inclination leads to inappreciable fluctuations on an axis, and as a whole doesn't influence on structure and stability of a vortex. So we can forecast tornado evolution and simulate interaction of such type of vortices. To make modeling, it's necessary to know the scale parities of parameters of the model and the real system which is simulated. This table shows such scale parities, and you can see, for example, these scale parities for tornado, tropical cyclones, and ocean vortices. Next application is vertical structure in a plasma. First example, quasi-particles or charged filaments in a uniform magnetic field. We studied the dynamics of charged filaments, which represent streams of charged particles in a uniform magnetic field using two-dimensional model of plasma of Taylor-McNamara. You can see the vortex structure formation at cross-section perturbations of the charged filaments. Figure A is one perturbed line, type evolution, and figures B and C represent two lines, dynamics for two-lines configuration with perturbations of the same and opposite polarities. Such perturbations lead to the formation of a magnetic field in a zone of polar custody that influence on the dynamics of streams of the charged particles. We have found that structures of vortical type are forming especially quickly and more intensely, that more amplitude of perturbations and quantity of the filaments participating in interaction, and also then is more close to each other filaments are located. Cross-section perturbations of velocity of the stream lead to its transition in an unstable state with formation of folds, you can see here, and complex vortical structures. Second example is vortices in dust plasma. The theoretical analysis and the experimental results show that in plasma with gradient of dust charge, the vorticity of dust particles can exist. This gives a possibility to study the interaction between the hydrodynamic vortex structures and dust particles, considering the dust particles as vortices of very small scale. You can see our results on interaction of dust particles with vortex for linear dust layer, left picture, and for dust plumes, right picture. So we have found that the character of interaction in this case depends on the value of particles' vorticity. If particles' vorticity is very small, then the interaction doesn't develop. When the vorticity of dust particles becomes like vorticity of the hydrodynamic vortex, the interaction becomes significant, and the particles are involved by a vortex in large-scale rotation. You can see in these pictures. Last example is evolution of plasma fluids in the ionosphere. Plasma fluids in the ionosphere are formed under influence of solar ionization of artificial injected barium in rocket experiments at heights of the F region of ionosphere. You can see the evolution of artificial electron-ionic ionospheric homogeneity cross-section of this homogeneity. One can see that such plasma structures that lead to formation that lie along magnetic field electron-ionic irregularities, mainly in collision plasma with small parameter b. Diffusing across magnetic field at evolution get irregular stream structure. It coincides with the experimental data obtained in rocket experiments. Such irregularities lead to development of nonlinearity in a F layer and can lead to dispersion and fading of high frequency and very high frequency radio signals. There are also many other physical systems which can be simulated using proposed approach. For example, the vertical and spiral structures in space and planetary plasmas, vertical motions in gas and fluids, and other. But we have not much time to discuss other applications here. Thank you.
Thank you, Professor Belashov. Now, discussions. Any questions? Please.
When considering the two-dimensional theory, you used the logarithmic function as the point, as the function of the point source, the green function. I want to attract your attention to the fact that in application of two-dimensional theory to graphene, people still use the colonic formula, 1 over r, instead of logarithm. And this is considered as more realistic, in spite of the fact that formula, it is logarithm. What do you think of this? All your results are based on using the logarithm as the point function of point charge, of point source.
I don't know exactly the graphene theory and experiments with graphene. I think my approach can be used also and also for modeling of other two-dimensional structures.
So, do you know how to predict the structure which is to expect? So, perhaps by the choice of initial conditions or something like this? Or you just take a question, you fix initial conditions, you apply your approach and see what comes out.
We use the scale parities between modeling vertical structures and real in physics vertical structures. And if we want to modeling real physical systems, vertical physical systems, we can use these scale parities and do modeling, make modeling our vortex structure, and after that use our result for interpretation and prediction of behavior of real physical systems.
Other question? If not, let's thank Professor Belashov.